Okay, so this is the proof we were working on yesterday. And again, we were talking the last couple of days that we want, at this level, we don't want to have to work on both sides if it's not necessary. Again, an identity is proven by starting with one side and showing that that one side is equal to the other side. So that says I'm just really working on one side and making the one side look exactly like the other side. So if we don't want to have to touch both sides, we're not going to. But in this example here, we got to a point where we were pretty much stuck on this one side. And you're going to get me back up to speed with where we were at yesterday. What was the first thing we did over here on the right-hand side? We distributed, right? We got cotangent u, secant u minus 1. And then what did we do with the cotangent secant? We broke it up, and what did we eventually get? 1 over sine u minus 1. And then I turned that 1 into sine u over sine u, right? So we got then 1 minus sine u over sine u. But then we looked at the other side. There's really nothing else I can do here. I've got this now expressed as one term, which is what we have over here, one term. But I can't do anything else here, and it's not obviously that. Okay, so this is an example where we are going to have to work on both sides. Okay? And as I look on this side over here, what might there be something I can do? And we kind of highlighted a couple things we could do. I mean, the first thing we did yesterday was say, is there something we could do on both sides? Yes, there was, but we decided we would start with this one. What was one of those things we said we could do over here? Something that we should always be looking at when we see that right there. Pythagorean identity, right? What is cotangent squared going to be equal to? Cosecant minus 1. Cosecant squared minus 1 over 1 plus cosecant. Okay? Now I'm thinking, well, why was that a good move? I just turned one term in the numerator into two terms in the numerator. But that's why Pythagorean identities are nice, because Pythagorean identities usually are always going to give me a dots factor. Okay? Do we have a dots up on top? Absolutely do. What is cosecant u squared minus 1 going to be? Not cosecant squared. Cosecant plus 1, cosecant minus 1, right? So I can factor the top. Cosecant u plus 1, cosecant u minus 1, all over 1 plus cosecant u. Something nice is going to happen now. Canceling factors, right? Cosecant u plus 1 and 1 plus cosecant u, does the order of addition make a difference? Absolutely not. They're going to be gone. I'm left with cosecant u minus 1. And are we at a point now where, from what we had yesterday, do we now have common ground? Did we ever have a cosecant u minus 1 on the other side? We did? Okay. And even if not, we're now one step away, because cosecant u is what? 1 over sine u minus 1, which we have right there. Okay, so even if we didn't, and Jared, you do say we've got a cosecant u minus 1 over here. Okay, so we're done now. We've found common ground. We have found common ground. Even if not, if we didn't have that, well, now I can change the cosecant u to 1 over sine u minus 1. And now this and that, I now have common ground. Have I proven the identity? Yes. Okay. Do we want to have to work on both sides? No. We don't want to have to work on both sides. Sometimes will we have to, though? Yes. We just want to show common ground. Okay. It's a lot easier for us to just work on one side. If I can get that one side to look like the other side, kudos to us. Okay. But sometimes we just can't. And in those cases, we're going to work on both sides. We are allowed to do that. We don't want to have to, but we can. And we just want to show that we've got common ground. Okay, so whenever I get to a point here where I've got something I've got over there, I can draw that to that. We have common ground. We have proven the identity. Okay? Questions on that one? Okay, what are a couple ones that we've got from homework that we've got question on? 24? Okay, so we're going to go off of what you guys do. So, Will, you asked the question, which side did you start with? Will started with the left side, and what was the first thing you did? Okay, so what do you have over here? So, say that again. Okay, so really the first thing you did then was you recognized that this is cotangent B plus tangent B. And then you said, all right, I did cosine beta over sine beta plus sine beta over cosine beta. Reasonable first move? Yeah, definitely. He's done nothing wrong. He's done nothing wrong. Parker, tell me something we could do next then. Yeah, it's indicated to us to do what? Addition. We can't add unless we have... Okay, tell me what it would be then. What would the common denominator be? Good, yep. Our common denominator would be sine beta, cosine beta. Okay, so Jared then, what are we lacking from this fraction on the left? Well, we got the sign, but we lack. We have the sign. What do we lack? The cosine. So what would cosine beta times cosine beta be? Cosine squared beta from the left. So this left fraction would become cosine squared beta over sine beta cosine beta. Emily, what does the right one lack? We lack the sine beta over here, so what would the top become? Sine squared beta over sine beta cosine beta. So we can't combine like terms, but when we'd add them together, we would get this. Okay, and now, Will, what do you recognize? Yeah, we've got the Pythagorean identity over here. We've got 1 over sine beta cosine beta, which is the same as saying 1 over sine beta times 1 over cosine beta. 1 over sine beta is cosecant beta times 1 over cosine is secant beta. Common ground without having to work on the other side, right? Okay? I want to work on the right-hand side. Okay? There's more than one way to do a proof. Always more than one way to do a proof. I want to start on the right-hand side. Paige, what would be a good move to do on the right-hand side? Break them down. Yep, secant beta is going to be 1 over cosine beta. We're doing it in a different color here. 1 over cosine beta times 1 over sine beta. So 1 over cosine beta sine beta. Okay. So did I pick a good side to start with? I didn't pick a good side to start with. There's really no more for me to do on the right, is there? Okay, so what would I have done then? Then we would have gone to the left, and on the left, would we have found common ground? Absolutely. Looking at this one, I would always start with an addition, subtraction over a multiplication, division. Why? Well, with addition and subtraction, we're probably going to turn into fractions, right? And with fractions, what do we have to have for addition and subtraction? The common denominator. So I'm always going to look to the side there where there's an addition and subtraction before I'm going to start with the side with a multiplication. Multiplication's easier. Okay? Okay? But again, don't erase what you've got over there. This is just a case where you're going to, if you started with the right, you're going to have to go to both sides. Okay? All right, with 24? Good there. Other ones we've got question on? 21? Okay, so Dawson, you asked it. I'm going to have you tell me where you started and what you did. I'm assuming you started with the left side, right? Why? What are you going to do on the right? Not much. Break it down into 1 plus 1 or 4 divided by 2. Where do you go? 2 is a lot of things. We're going to start on the right-hand side, or the left-hand side, right? Okay, so tell me what you did first then, Dawson. Yeah, you've got a binomial being squared, so you FOILed these out. Tell me the results of your FOIL. Yeah, we're going to get cosine t sine t, but there's going to be how many of them? 2 of them, so minus 2 cosine t sine t's plus a sine squared t. Okay? Now over here on the other side, then, let me kind of keep that as the quantity so we can clearly see the 2 sets that we got. What are you going to get from this FOIL? Everything is going to be a plus sign. Yep. So you're going to get a cosine squared t plus 2 cosine t sine t plus a sine squared t. Okay? So that's a definite first move. The first thing you got to do over there is you've got to FOIL those out. Okay? You just got to be careful of your FOIL. Okay? What should we do next? Well, combine like terms, right? We're adding and subtracting. We've got to combine like terms. Are there any other cosine t's or cosine squared t's? How many? We have 2 cosine squared t's. Do we have any other cosine t sine t's? One's negative 2, one's positive 2. They're going to knock each other out. Any other sine squared t's? A positive 2 sine squared t. 2 terms, they share what? They share a 2. We're going to factor that 2 out, which leaves me with cosine squared t. And once I factor out that 2, I am left with the Pythagorean theorem, cosine squared plus sine squared is equal to. Important step to show right there, though. Okay. And now we've got the identity proven. Cosine t minus sine t squared plus cosine t plus sine t squared will always give us 2. Will always give us 2. Problem with the FOIL? Yeah. Yes. Okay. Numeric problem with the FOIL. Other questions? Page 30. Okay, Paige, which side did you start with? Start with the left side, and again, I would agree this is another case like that first one. I'm always going to start with an addition subtraction before I start with a multiplication. So we're looking at the left-hand side, and then tell me, go ahead, what was the first thing you did over there? Okay, so you replace tangent squared with? Sine squared theta over cosine squared theta minus sine squared theta over 1. That's definitely a legit first step. Okay? So now then, Emily, regardless of how you started this, what would you do next if this was your first step? What would you do next? Yep, same as Parker's one, right? We're going to subtract fractions. We can't subtract fractions unless we have, and what is that common denominator going to be? Cosine squared. So this is all going to become 1 fraction over cosine squared theta. Okay, so Emily, does the 1 on the left already have what we need? Yep, so it's just going to stay a what? Sine squared. Okay. Jared, what do we lack on the right fraction? Okay, so what would the numerator become then? Good. So minus sine squared theta, cosine squared theta. Very good. Okay. So now I've got one single fraction. Dawson, I recognize something in the numerator. I recognize something about those two terms. They share a sine squared, right? What can we do with that then? We could factor it out, right? We could factor it out. So if I factor that sine squared out, sine squared theta, what would I be left with? 1 minus cosine squared theta, right? Over cosine squared theta. Okay. And now again, I've always got my goal in mind. I've always got my goal in mind. Well, what does my goal have? It has a tangent squared, right? Well, do I have my tangent squared now? Where's the tangent squared? Sine squared over cosine squared. So if I separate this out, it would be, and you wouldn't have to write this step, but I'm going to show you the steps here that I'm doing. Sine squared over cosine squared times 1 minus cosine squared. And what is that sine squared over cosine squared then? That's our tangent squared. And now what do we have right here? The Pythagorean identity. 1 minus cosine squared is sine squared theta. Okay. Where did you get hung up, Paige? The factoring? Okay, and again, factoring is always something you should look for as well. You know, if I've got multiple terms, if I've got more than a monomial, always look to see if there's something we could factor out. Always looking for what first? GCF, dots, general trinomial. Okay, factoring is common steps on these ones. Okay, I want to take a look at one more because I want to get into the next section. Is there someone that hasn't asked a question yet that has one? Jared? 9, we can look at 9. Keep your questions until tomorrow. I just don't want to spend the whole day today going over identities and not getting into the new ones at all. So if you've got more, hold them. Or now that we've gone over some, go back and look at them now and see if you can get through them. But number 9, we want to tell whether or not f of x equals sine x is an identity. Okay, so in number 9 we've got sine cubed x times 1 plus cotangent squared x. And what is the f of x going to get replaced with over here? Sine x. So we want to see if that's equal to sine x. Okay, so my goal over here is to have sine x. Okay, tell me what you did first, Jared. Pythagorean identity. Yeah, we've got the red flag for it with a 1 plus a square. It worked out. So we've got sine cubed x times secant squared x. Great, first step. Okay. Nothing else we really could have done there first. I guess we could have distributed, but eventually we would have come back around to this again. All right, what should I do now then? Convert, right? I'm going to convert it. So this is going to be sine cubed x. I'll go ahead and put this over 1 because I'm going to put this as a fraction. And what is secant squared going to be? 1 over cosine squared x. Yes, I'm sorry. Shoot. That's our issue right there, Jared. It's not secant squared, it's cosecant squared. The two c's go together. Yep. Thank you for bringing that up. I don't know why I missed it. Thank you. Okay, so this is 1 over sine squared x. The square is going to cancel the cube and leave me just with sine x.
I read the wrong one.
Okay, all right. Go with 9. Okay, so again, if you've got more questions, I want you first to look back at them after we've gone over a couple of them now and see if you can figure it out for yourself again. But if you still can't, we'll have time to ask tomorrow. But right now I want to get into 5.3. And 5.3 is all about the sum and difference identities. And I think Will brought this up yesterday. He said, aren't these on our Regents reference sheet? Yes. The sum and difference identities are on the Regents reference sheet. We had the sine, well, let me start off with the cosine. We had the cosine of an angle A plus and minus an angle B. And then we also had the sine of an angle A plus or minus an angle B. The question is, do you remember them? These were the ones where sometimes, obviously, out of all four of these, out of all four of them, there's a cosine A, B, and a sine A and B for each one of these. Each one of these has a cosine A, a cosine B, a sine A, and a sine B. Down here we have a sine A, sine B, a cosine A, and cosine B. And how we tried to keep these apart last year is that some of them, the trig functions were together as a cosine A, cosine B, a sine A, sine B. Others, they were mixed up. We had a cosine A with the sine B, and then the sine A with the cosine B. Okay? Do you remember in which pair the trig functions were together? Cosines. Cosines had the trig functions together, but the operations were what? Same or opposite? Opposite. So with cosine, our trig functions were together, but our operations were opposite. With sine, the operations were the same, but the trig functions were mixed. Okay? So cosine A plus or minus B was equal to, our trig functions were together, so cosine A, cosine B, sine A, sine B. But our operations were opposite. So instead of having a plus minus over here, we're going to have a minus plus. The addition over here with cosine is going to be a subtraction. The subtraction with cosine is going to be addition. And now down here, our operations are the same. It's still going to be a plus minus, but our trig functions are going to be mixed together. We're going to have a cosine A sine B. That's got to be the other way around, my bad. Sine A cosine B. Plus and minus sine B cosine A. And that's how we remembered them last year. Okay? With cosine, my trig functions were together, but the operations were different. With sine, they were mixed, operations were the same. Okay? And I don't remember if I showed you the proof or not last year, and if I did, I'm going to repeat it. If I didn't, so be it. This is where it comes from now. Okay? We want to prove, and we're just going to do the proof for the cosine of A minus B. The other three are pretty much following the same process. So we're going to try to prove the identity here that the cosine of A minus B is equal to the cosine of A times the cosine of B plus the sine of A times the sine of B. And what we're going to do is just follow along with this one. So let's take a look at what we've got here. We've got this unit circle. What's the unit circle mean? Where's it centered at? Centered at the origin. It's got a radius of what? 1. Okay, so we've got this unit circle. And I've defined this angle A as being a second quadrant, and it could be anywhere. It could be first, it could be in the second, third, fourth, wherever. But we've got this standard position angle A. I then have this standard position angle B. Same thing, it could be anywhere. Okay? Well, this angle in between them, how would we find the measure of this angle that's in between them? We would subtract the two, right? We'd go all the way out to A and subtract off the B. So if I subtracted the B off of the A, that would be the angle that's in between them. That would be my angle A minus B. Is everybody comfortable with that? Okay? Well, defining the points on the unit circle then. Every coordinate on the unit circle, every xy coordinate on the unit circle can be defined in terms of the sine and the cosine of the angle we're looking at. The x-coordinate is related to which trig function? Cosine. The y-coordinate is, and we remember that by thinking alphabetically. Cosine comes before sine, the x-coordinate comes before the y-coordinate, the x-coordinate is cosine, the y-coordinate is sine. So again, out here, we're looking at angle A. So what is this coordinate right here? Cosine A, sine A. What is this coordinate right here? Cosine B, sine B. Is everybody all right with that? Everybody's good there? All right, so what we're going to do is we are going to find this distance right here, the distance from P to Q, those two coordinates that we just found. We're going to find that distance using two different things. The first thing we're going to do is we're going to find that distance using coordinate geometry from geometry. We have a distance formula in coordinate geometry. That distance, do you remember what your distance formula is from coordinate geometry? Square root of? Yes. Change in x squared plus change in y squared. Now how do you find a change in values? You take their difference. You take their difference. Okay? So what we're going to do, and I'm not going to show you the next page, and I'm just going to write it down for us. Our distance formula is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And if you can remember from last year, did I ever make you try to remember that? No, I never did. Why? It's just the what? It's just the Pythagorean theorem, isn't it? That is just the Pythagorean theorem. A squared plus B squared. Where's the C squared coming from then? We would undo the radical by squaring, and then this would be a D squared. This is just a Pythagorean theorem. I'd never, ever, even if I was a geometry teacher, would never, ever make you know that formula. It's the Pythagorean theorem. It's the Pythagorean theorem. When you leave high school, are you going to remember the Pythagorean theorem? Probably. Are you going to remember the distance formula? Not necessary, right? Okay, so this distance from P to Q, and I'm going to call it PQ squared. Is everybody all right with me calling the distance PQ? Is that right with me undoing the radical and making it a square? Okay, is equal to, okay, well, what's my x2? I'm going to call my x2 the cosine B. Really doesn't make a difference here. Cosine B minus cosine A squared plus, over here, we're going to have same order, sine B minus sine A squared. Okay, and now how are we going to deal with these squares? And we're going to FOIL them out, then we're going to, if possible, combine like terms, right? We're going to FOIL them out, we're going to combine like terms, and I'm not going to do all that algebra for you here, but when we do that, we are going to get something that looks like this. Okay. So here's the cosine A minus cosine B squared plus sine A minus sine B squared. We run the FOIL. Cosine squared A minus 2 cosine A cosine B plus cosine B squared. I'm glad Dawson asked that question on this one because we saw a proof where we had to do a similar thing, right? Okay? Sine A minus sine B squared. Well, that's going to be sine squared A minus 2 sine A sine B plus 2 sine squared B. Okay, well, what do we have then right here and here? What is cosine squared A plus sine squared A? 1. What is cosine squared B plus sine squared B? 1. 1 and 1 gives us 2. So 1 plus 1 is 2. And then what's left? These both have a what? A negative 2. So I'm going to pull out that negative 2. Cosine A cosine B plus sine A sine B. Okay? So PQ squared is equal to 2 minus 2 cosine A cosine B plus sine A sine B. Are we all right with that? Okay, now, how else are we going to find the distance? The other way to find that distance is take a look at what we've got here, folks. What do point P, point Q, and point O make up? They make up a triangle, right? What's the Pythagorean theorem for any triangle? Which law? Which law, sines or cosines, is the Pythagorean theorem for any triangle? Law of cosines. If I know what this side is and what this side is, and do I know what OQ and OP are equal to? What are they equal to? Y. It's a unit circle and their radii of the unit circle. If I know these two sides and the included angle, what is the measure of this angle right here? A minus B, right? If I know two sides and the included angle, law of cosines will allow me to find the third side. Law of cosines tells me that the square of my third side is equal to the square of my first side plus the square of my second side minus 2 times of the product of the first and second side times the cosine of the included angle, right? I now have two formulas, both finding what measure? Both finding PQ squared, right? Well, is that PQ squared different for the law of cosines as it was for the distance formula? It's the same side, right? Well, if I have two different things that define PQ squared, what can I do with those two different things? I can set them equal to each other, can I? Okay? So, I'm going to set these two things equal to each other. This 1 plus 1 minus 2 cosine AB that we just got from the law of cosines, I'm going to set equal to this 1 plus 1 minus 2 that we just got from down here, right? I'm going to set them equal to each other. Well, they both have a 1 plus 1, right? Well, what's going to happen to those 1 plus 1s? They're going to knock each other out. Negative 2 cosine A minus B is equal to negative 2 cosine A cosine B plus sine A sine B. I'm now just going to divide both sides by. Knocks those out. What is cosine A minus B equal to? Cosine A cosine B plus sine A sine B. Okay? We didn't go through that last year. Were we at a level where we could have, though? Does everybody completely understand how we can prove this? Okay? So it's not just some identity that's out there in the air, me telling you to use it. Can we see where it's coming from now? Okay? We're just using two different formulas to define a length. We're using the law of cosines because we recognize it as being a triangle. And the law of cosines allow me to find any angle of a triangle. I used coordinate geometry because I knew those two coordinates, so I can use those two coordinates to find the same distance. I set those two distances equal to each other because they're equal. They are the same thing. And that allowed me to then work it down and solve for the cosine of A minus B. So cosine A minus B is equal to cosine A cosine B. My trig functions are together, but my operations are opposite. Okay? The one for plus is very similar. The one for the sines are very similar. So I'm not going to go through 4 derivations. If you understand this one derivation, hopefully you're pretty confident in finding the other 4. Okay? So, knowing that then now, I'm going to go ahead and take us to here. In Algebra 2 we had A's and B's. Here they're using U's and V's. Is that going to throw anybody off? so hopefully not. So there's our cosines for the sum and difference.
Everyone you can donate, please bring it to the course room.
Here's our sign for the sum and difference.
7th and 8th grade students. Franklinville Youth Football and Cheerleading sign-ups will be held this Saturday, May 2nd, from 10 to 2 at the Franklinville American Legion. Following students, please report to the office. Taylor Wilson, Savannah Batcher. Zach and Tyler McManus, please report to the guidance office. Thank you for your attention.
Okay, 75 degrees. Is that one of the special angles that I know, like the back of my hand? It's not. But is it the sum of two angles I know, like the back of my hand? Absolutely it is. 75 is what plus what? 45 plus 30, right? Well, this is the same as saying the cosine of sum A plus B. Do we have an identity for the cosine of the sum of two angles? Absolutely we do. But instead of having A, we've got 45. And instead of having B, we've got 30. So expand that out for me, please. What is the cosine of 45 plus 30 going to be equal to? Cosine of 45 times the cosine of the 30 minus the sine of both of them. Sine of a 45, sine of a 30. I know all four of those function values. Sine and cosine of a 45 is what? Radical 2 over 2. What's the sine of a 30? The sine of the 30 is the easier one. 1/2. What's the cosine of the 30? I can now find those two products and then take their difference, and I now know an exact value, not only for 75, but every multiple of 15 degrees now. Because I can find 15 by taking what? 45 minus 30. I've got 15. I already knew 30, already knew 45, already knew 60. Now I know 75. I can now find the exact value of every 15 degrees. Have a good one, folks. We will see you tomorrow.